Now we know how to fit the line model. We know how to find the orientation of the line that minimizes sum of squared errors. But how to evaluate the quality of this model? Of course, you can use sum of squared errors, but sum of squared errors is a bit difficult to assess because, first of all, it has squared units, and then we don't know how big, how small it can be, for example, because sum of squared errors also depends on, for example, sample size, right? How many points you have, how many data points you have. So now let's talk about these statistics that tells how good your model perform on your sample, and that's what we call the figures of merit. So figure of merit, it's a statistics that tells something about performance of your model, how good your model is. So let me first of all remind you what we have. We have this little example, a very simple example with sample size equal to 5. We have one x variable, its height of people. We have one y variable, its weight of people. And you remember in the previous video, we learned how to actually fit a model to this data, and then we got the predicted y values. Okay, so all figures of merits are based on the difference between the predicted and the reference values, the real y values, or errors of prediction. Now let's first of all compute the errors of prediction. So remember, error of prediction is simply a difference between the true, measured with some reference method y value, and the predicted value. So for example, if you take this one, the true value is 55. The predicted value is 57, so the error of prediction is -2 in this case kilograms, right? So now we can use all these errors in order to make an assessment, to calculate different statistics, right, about these errors. Well, first of all, in a good model, the predicted and the reference values must be as close as possible to each other, right? So it means that we can simply assess how close the y and yp values are. Then, and this is just a consequence of the first bullet, right? So the residuals must have a small variation. So the variation of these residuals values should be as small as possible, and we know how to estimate variation, right, already. And then finally, the residuals must be random, and if they are random and if they are numeric and random values, we of course expect normality, right? So normally distributed, but of course in this case we have only 5 residuals. 5 residuals cannot be normally distributed. In this case we say they came from normally distributed population, right? So these are 3 main things that we need to evaluate using either plots or statistics. So how close y and yp values are, how big the variation of residuals, and if residuals look normal and random and normally distributed. So there are, as I said, visual tools and statistical tools. The visual tools includes 3 different plots. The first plot is predicted versus reference values, then residuals versus predicted values. It's both scatter plots, and then the cuckoo plots for residuals to check the normality. The statistics include standard deviation for residuals, aka standard error, because in this case it's a statistic of statistic, right? So you calculate standard deviation of residuals, and residuals is statistic. So that's why we call it standard error of residuals, or standard error of prediction. That tells you something about variation of your values. Then you have coefficient of determination. We will discuss it in a minute. And then also we can make an F-test, similar thing that we did in ANOVA, and find out how likely actually these predicted values, the values that our model explain, how likely they are just random, or maybe they indeed have some systematic variation. Okay, so 3 statistics and 3 plots. Let's start with plots. Well, predicted versus measured or versus reference values plots, it's kind of easy. You simply make a plot, a scatter plot, where the x-axis will be the real y values and the y-axis will be the predicted y values. This is how the plot looks like. For example, what this point is, right? So this point has the reference y value is 55, is this one, right? And the predicted y value, you can see it's a bit bigger than 55, so it's 57. So you have 5 rows, you have 5 data points, and for every data point you have 2 values, y and yp, the real value and the predicted value, and therefore you can make a scatter plot. So in this plot we have this expected line. This is the expectation. The slope of this line is equal to 1. Why it's 1? Because if it's 70 here, then it should be 70 here. If it's 80 here, it should be 80 here, right? So the slope should be equal to 1. And of course, intercept of this line should be equal to 0. So this is the theoretical ideal line. The closer the points are to this line, the better, right? So that's how to assess it visually. The second plot is used to check the randomness of residuals. So strictly speaking, the residuals should not depend on your y values. They should be completely independent, completely random. And this is what we assess with the second plot. You can see in this case we have the predicted y values and the residuals. And these points should be just randomly scattered on this plot. You should not see any clear patterns, clusters, and so on. Of course, when you have 5 points, it's a bit difficult to assess the randomness. But when you have, for example, 10 or 30 points, then this plot makes more sense at least. Okay. So again, it's a scatter plot. In this case, the x-axis of this plot is this values, and the y-axis of this plot is this values. For example, again, if you take this one, it's 57 predicted value, and then you can see it's -2, it's the error of prediction. Okay. Finally, the last plot, you already know it very well. It's a QQ plot, or quantile normal probability plot for residuals. Because we assume that all these values should be normally distributed, we can make a QQ plot and check this normality. Again, for 5 values, maybe it's not very efficient, but indeed, for example, in this case, we clearly see the normal trend, right? So this is just a QQ plot that you already used many times, and then these are the values that I used to make the QQ plot. So in this case, we can supplement this QQ plot, of course, with Shapiro-Wilk test, so we can test for normality. And for example, in my case, you can see a p-value very high. So in this case, we cannot reject null hypothesis. We can assume that indeed residuals came from normally distributed population, which is actually one of the main requirements for your linear models. Because when we make linear models, the ordinary least squares algorithm assumes that your residuals are normally distributed. So these are 3 main plots together. Now let's talk about statistics. First of all, you remember that average y value is 70, but average yp value will also be 70, right? However, the average residuals is 0. And that's one of the consequences of using this OLS algorithm, which fits these points best. You always have average residual equal to 0, so it means that you don't need to compute average. You don't need to compute average. So you just need to take a sum of squared values. Now let's do some calculations. Well, first of all, I compute the distances between y and average y. Then I compute distances between predicted y and average predicted y. In this case, it's the same 70, right? For example, how I got this -25. You remember the average y is 70, so it's 45 minus 70, it will be -25. How I got this -26? Again, average yp is 70, it's 44 minus 70, it will be the -26, right? And then I can also just use the residuals. In this case, I don't need to subtract average because I know that average is equal to 0. So in this case, E and E minus ME is the same value, right? But you can treat it also as a distances. Then the idea is that these values, the values, the real values, it's a sum of these and this, right? And then you can see indeed, if you have -26 plus 1, you will get -25, right? So the idea is that you have explained part, the part that model explains, so the systematic variation of your y values. And the residuals is what model does not explain, so it's a random variation of your y values, right? Now let me continue. First of all, I just want to remind you that this way of expressing the values as a sum of explained part and residuals part, we also already used, for example, when we make a t-test and check for normality. Remember that this is the values we have, and this is the effect, right? So this is the values, this is the y values, let's say, and this is the groups we had in this t-test analysis. But the idea was the same. This is an effect that we estimate, because in this case we have only 2 groups, so the effect, we model the effect as average values, right? And then this is the residuals, which is a difference between the effect values, the systematic effect that we estimated, and the real values that we observe. That's what we did in t-test. But later we also did it for ANOVA. You remember, these are all values. Then we had a bias, right? And then we have a systematic part. It's, again, the average values in this case. And then we had residuals, which is a difference between the real values minus bias and then minus systematic part. It gives you the residuals, right? So my point is that presentation of your data values in this way, so you have a sum of systematic part and residuals, it's very common. And you can see it in many different methods, right? But let me get back to original data. So this is the original data, just distances, right? So we subtracted this bias. This is the explained part, systematic part that model explains, and the residuals, it's what model cannot explain. Variation of your y values that model cannot explain. Now we can use the same idea, for example, like in ANOVA. So in order to estimate, for example, variance, we need to take a sum of squared distances. So these are sum of squared distances for the total y, for the predicted y, and for residuals. You can see that the residuals have a very small sum of squared distances. Now look, this sum of squared values, because we have like 3 different sum of squares, I will use a special notation here. So this will be SSYY. It means sum of squared distances between y and average y. This is, I use SSPP, meaning sum of squared distances between the predicted values and the average. And then this is just SSE, because I don't subtract average in this case. It's just a sum of squared errors. So this is why the index is single here. Okay. Now, in order to compute variance, I need to divide sum of squared distances to degrees of freedom. Let's recall that originally here I have 5 degrees of freedom, right? But then I lost 1 degree of freedom because I calculate average, and then I subtract average from these values, right? So I reuse these values. So now it's 4 degrees of freedom. Now, how many degrees of freedom I used here? Well, in this case, I used 1 degree of freedom, right? Why? Because how I got these yp values? I got these yp values by simply multiplying the x values to b1, right? So, and to estimate b1, I just use 1 degree of freedom. And then finally, how much is left? It's 3 degrees of freedom. You can ask me where the b0 is. Well, b0 is here, so you remember that we subtracted b0 already. So actually, minus 1 degree of freedom here, it's responsible for b0, and minus 1 degree of freedom here, it's responsible for b1. Because how to get y values? Y values we get by taking y minus b0 minus b1x, right? So you can see that first we lose 1 degree of freedom here, then we lose 1 degree of freedom here, because both b0 and b1 are estimated based, you remember, on the statistics of your sample, right? Average, covariance, and variance, and so on. So that's why here we have 3 degrees of freedom. So it's n minus 2, because you need to estimate 2 coefficients and use these 2 coefficients in order to get the residuals. Now we can compute the standard deviation of residuals, so standard error, right? So how? Well, you remember first we compute variance by taking ratio between sum of squared errors and the degrees of freedom, and then we take a square root of this variance. So this is how to do it. 10 divided to 3, it's 3.33333, and then square root of this will give you 1.826. So this is standard error, or it's a standard deviation of your errors, of your residuals. Then I will put it here, keep it here for a while, hidden. Now let's compute the next statistic. It's a coefficient of determination. So coefficient of determination is also based on all these variants, but the idea of coefficient of determination is to make a unitless estimation of this variance. So these values have the same units as your y values. So in this case, it's kilograms. You remember we predict weight of people, so it's 1.8 kilograms. Standard error is 1.8 kilograms. But coefficient of determination, it's a kind of a percentage. So let me calculate it first and then explain. So the idea is following. You take a sum of squared errors, and then you divide to a sum of squares for the real y values. Why you do that? What's the meaning of this ratio? Well, it's simply a percentage, right? So it's a ratio of 1, of course, but it's a part, how big 10 is comparing to this one. So it's a percentage, how much of error as a percent of sum of squared y values, sum of squared y distances from the average, right? So remember, this is the sum of squared distances between y and yp, and this is sum of squared errors. So how big variation of errors is comparing to the variation of y values around average. And then, for example, in this case, you can see it will be a very small number. But r squared shows you the opposite, how much we can explain. So how much is this? Not this, but how much is this in percent? So in this case, we subtract this ratio from 1, right? So in this case, we simply take, first of all, we compute the residual percentage, how big the residual variation in percent, and then we subtract it from 1, and that's what we have here, and this is the result, right? What's the meaning of these two numbers? This number, you remember, it's this ratio between these two, this one and this one. This number, it's a percentage of residuals compared to the variation of y values. So the error, it's a 0.6% variation of your error It's 0.6% of variation of your residuals, or variance of your residuals, right? And this is the explained part. This is how much of model can explain. It means that variance of all yp values is 99.4% of the variance of your original y value. So you can explain 99.4% variation of your y values by using this model. So the residual, the part of the variation that you cannot explain, it's 0.6%, so it's very small. So this is coefficient of determination. It tells you how big the portion of y variance can be explained by the model, or can be explained by your predictor, because that's how you use the model, right? Your predictor, you use predictor to get the y values, predicted y values. Okay. So again, I keep it here. And now I can also make a f-test. You remember how f-test works. This looks similar to one-way ANOVA. So you have explained part, you have residual part, and you remember f-value, it's a ratio of variance of the explained variance to the residual variance. So let's compute it. So this is the ratio. This is how to compute f-value. So the mean squares, it's simply when you take sum of squared values and divide to degrees of freedom. So this is the mean squares. Sum of squared values divided to degrees of freedom. So this is the mean squares of variance, right? And then you take f-value as a ratio between this value and this value. So it tells you how big the ratio, or how much bigger the systematic variance compared to the random variance. You can see it's 507. We expect it to be 0. If model doesn't work, it should be 0. We got 507. Of course, it's almost impossible to get it just by chance. And then you remember that f-value follows f distribution. So it means that we can use this distribution to compute a p-value. And this is the p-value, remember. So this is the f-value. We have degrees of freedom for systematic part is 1. Degrees of freedom for random part is 3, right? And you remember that we take the right part, because that's the direction of extremeness. And then you can see that the p-value is very small. It's 2 out of 10,000. It's a very small chance that we observe this effect just by chance. So in this case, f-value confirmed that we have a pretty good model. It's very unlikely that this model, these coefficients, these meaningful coefficients are taken just by chance. Okay. Now let's check that our calculations are correct. I will simply do these things in R. So this is x values, this is y values. This is how to get the model. We already did this, but this time you can see I saved this model to a variable m, because variable m contains all information about coefficients, about statistics, and so on. And you can show this information if you run summary m. So this is how it looks like. I hide all this unnecessary information with a gray color, so we will come back to this information later. But so far you can see that these are our regression coefficients, exactly the same as we got manually. And then let's look at the statistics. Residual standard error 1826, and this is exactly what we got here. 3 degrees of freedom. You remember for residuals we also had 3 degrees of freedom. The R squared value 994, 994. The F statistic 507, 507, and the p value you can see 0.002 if we round it to 4 decimals, and that's what we get here. Okay. So far, all statistics that we calculated manually together, they match all these statistics that we can get using R. Okay. So now at least you know how to calculate statistics, how to use them, the meaning of these statistics. So what do they provide you? What kind of information you provide you? And remember that it's always a good idea to start with plots. So make a reference versus predicted values, make a residuals plot, make a normality plot. So by doing that, you check if your y values and yp values close to each other, if residuals are randomly distributed, and if they are normally distributed. And then this tells you something, some numbers that show how good your model is, how well it performs. So this is just a p-value for Shapiro-Wilk test. Okay, so far so good. However, there is a little problem here. All these statistics show how well your model performs on your sample. And you remember, we want to use model later for new sample, for new measurements. We want to predict values for the new measurements. Will your model be as good as this one for the new measurements? Well, apparently not, because we also have this sampling error. How to handle this? How to adjust all these statistics based on also sampling error? How to evaluate all these uncertainties caused by sampling error? That's what we are going to talk about in the next video.